The second approach to the concept of transfer function, the second way in which we can define and interpret the transfer function, arises from the ideas of the impulse response, and also the operation of the convolution, So the impulse response of a system is simply its output when the input to the system is a unit impulse function, which we denote with delta of t, and also when all initial conditions are 0. Well, in that case, with that input and initial condition 0, the output, which we denote with g of t, is the impulse response. But what is a unit impulse function? What is this delta of t? Well, the best way we can define it is by approximation. Let's begin with the concept of a pulse function. A pulse function is just the result of adding two unit steps. One with amplitude a here, and the second one delayed with the same amplitude but opposite sign, and delayed a certain time t. So if we add those two steps, we get, this is time, we get the unit the pulse function, this one here. This function is defined by, well, let's call it p of t. This is equal to just a when 0 is less than or equal to t, capital T, and 0 otherwise. This is a pulse. Well, there's a special case of the pulse in which we want this area to be 1. So if this is t, to do so we have to replace this a by 1 over t. So here we have 1 over t. And in that case the pulse has unit area below. Now, if we want to shorten the length of the pulse, but also we want to keep the condition of unit area, we get this kind of signal. Higher, but with less duration. This is the new t, and this is the new 1 over t. And if we keep doing that, if we can keep shortening the length of the pulse, we get a function infinitely short but infinitely high, and we denote it. Let me choose another color. We represent it with a thick arrow, and this is the unit impulse. So the unit impulse is simply delta of t is just the limit of p of t when capital T tends to 0. That is the limit when capital T tends to 0 of the previously defined function. Now, if we somehow are capable of introducing this function to the system, well, when all initial conditions are 0, and we're capable of registering the output, whatever output we get. Let's say this is the output. Then this output is all the information we need to know the response of the same system to any other output. Again, this function here is anything we need to know the response of the system, not only to delta of t, but to any other u of t we can think of, as long, again, as all initial conditions are 0 also in those cases. But how is that? How is that true? Well, because once we have g of t, the output of any other input, u of t, the output to any input u of t is given by the convolution of u of t and g of t. So the output y of t is given by the convolution of g of t, and remember, convolution is an asterisk, the new input, which is, if you remember the definition of the convolution, the integral from 0 to t of g of t, the impulse response, times u of t minus tau d tau. Well, in the next video I'll try to show why this is the case, but for now just trust me on that, and let's reckon what the consequences of this are in the S domain. If we apply the Laplace transform to this expression, well, here we just have y of s. And now, if you remember, if you've seen the videos on the properties of the Laplace transform, you probably remember that the convolution turns into simple multiplication in the S domain. So this is just g of s times u of s. So the convolution turns into multiplication of these two functions. And now you can see that, just as in the previous video, we can get the transfer function, the Laplace transform of the output just by multiplying the Laplace transform of the input by this g of t, by the Laplace transform of the output of the system when the input is a unit impulse. Again, the Laplace transform of the output is the Laplace transform of the input times the Laplace transform of the unit impulse response. So, as you see, the transfer function of a system, quite amazingly, is just the Laplace transform of the impulse response. And this is an alternative definition to the one we already have, but both obviously state the same thing. So the only thing we still have to prove is that this is actually true, and we'll do that in the next video. But for now, I'd like to remark. I like to make a remark or to emphasize the difference between a dynamic system and a static system, because now we know how to calculate the output of a dynamic system. Let's think of a system whose output is given, for example, by this law, by this rule. The output y of t is just 2 times the input y of t, u of t plus 1. Okay, this is a static system, and maybe we can think of a dynamic system, which is defined, and this is an external definition, by the convolution, we already know that, of the impulse response and the input. Well, if the input, if we have here some input to the system, some, I don't know, this input, well, here the output of the static system would be just at each point of time, I'll switch colors, I'll change colors, the same function multiplied by 2 and then added 1. I don't know, maybe this is the shape of the new output. And in the case of the dynamic system, I don't know what the output would be. I don't know, maybe this would be the output. But if we introduce a second input, if we repeat the experiment with a different function, we must focus, or we can focus on this point here, in which the two functions, the two inputs are the same. Well, in the case of the static system, the output, the two outputs will also be the same at that point, because the output of the system depends only on the value of the input at that particular point of time, and that is why the system is static. Whereas in this case, the fact that the two inputs coincide in some point doesn't really matter concerning whether the outputs are the same or not. I don't. Maybe this is the output to the second input, and here and at that point of time they don't have to be the same. They may be different, because the output of a dynamic system depends on the value of the input at that particular time, but also in all the previous values of and all the previous history of the system, so to speak. And this is why here we just use algebraic equations, and here we normally have either differential equations or convolution between signals, because they express this idea of being dynamic. Well, hopefully this makes sense, and I'll see you in the next video in which I'll try to show why the output of a system is given by the convolution of the input, of any input, and the impulse response.